Alright, welcome back guys. We're talking about now section 1.2, not the prelude, but the actual, which is going to be graphs of equations. Our objective is going to be finding x and y intercepts of graphs, graph using symmetry, testing for symmetry algebraically, and then writing equations of circles. And a quick question to kind of hammer the concept home about graphs in general is if I want to know if some point, -2, -6 for instance, is on the graph of some equation, which maybe not is the most obvious equation, what it's going to be if we were to graph it. Well, we could go through the laborious task of actually graphing that. Of course, there are definitely other ways of doing that. For instance, well, just algebraically, we can simply plug in the x and the y coordinate of the point into the equation and see if we get a true statement or not. So that's what I'd like to go about doing here, is we plug in the -2 in for x, and then the -6 in for y. So right there, we just simply take the product of the two, and then it's going to be equal to our x, which is -2, square that guy, add an 8 onto it, and then we're basically just asking ourselves, hey, does that work? Okay, so once we got that, of course, that gives us a positive 12 on that side. -2 squared, remember, don't let your calculator lie to you. If you type that in your calculator without the parentheses, it's going to tell you -4 because your calculator is stupid and just a hunk of plastic. So you got to make sure you tell it the right thing to do, and that is a positive 4 there, and plus 8, and of course, well, yeah, 12 equals 12. So basically the answer to the question is that point on that graph. Well, the answer is a big ol' yes. Okay, now we're going to get into the objective itself and we'll go about finding intercepts, specifically x and y intercepts. Alright, well, first of all, if you're going to be finding intercepts, realistically, it's just an aid in graphing. Now granted, what we just did in our last lesson is we worried about different shortcuts, about finding different ways to graph different equations, but these equations pretty much were in kind of a nice form to work with. So if you have something that's outside of that form, you might need a little help in getting the graph put together, and if you can algebraically find the intercepts, then that gives at least maybe some points to work with to get an idea what the graph is going to look like in case you're not sure. Alright, so anyway, moving on to the actual work now. If I'm finding x-intercepts, well, one thing, any x-intercept you've ever seen in your entire life is on the x-axis, and what that means is the coordinates of that point are some number comma 0. Okay, and that alone is enough to kind of at least get me rolling in the right direction here. If I have a 0 here as my y coordinate, that means I can plug in a 0 for the y, and then basically just roll out the rest of the equation as it is. X plus 1 minus 5, absolute value, that is, over there in the x plus 1. And then that's just an equation you can solve. I'm going to get a little tricky just here to get things in a nice format, is I'm going to take the 5 to the other side, but then I'm going to rewrite the equation in the other order just to make things look a little nicer. So I'm going to leave the 2, absolute value x plus 1 over here on the right, and then that positive 5, actually that's the left, this is the right, but you get the idea. Dividing through by the 2 gives me absolute value of x plus 1 equals, I'm going to go with the decimal version of this one. Of course you can use the fractions if you'd like. And then, of course, absolute value, we can split into two separate equations to get our two separate answers. So, -2.5 there. Alright, so the answer for this kind of depends on what you're looking for. If you're looking for ordered pairs, like as I subtract 1 from both sides here, I'll get a 1.5 and I can write that as 1.50. But sometimes when you're specifically talking about x-intercepts, you don't really worry about that other half of the point that's going to be the 0. So all you need is the actual value like that. And so I'll leave it to you to write it either way you like. I'm going to be lazy and just write the x coordinate and kind of go with assuming that the y is 0. Same thing over here, subtracting 1 from both sides gives me a -3.5, which I could write as -3.50, but I'm going to take a little bit of a lazy route and stick with that for my x-intercepts. Then the y-intercepts, same basic idea. If it's a y-intercept, that means my x-coordinate is 0, and then my y is, some other number. And so again, armed with that information, I can replace now the x with 0 and leave everything else as is, and then figure out what y is. So 2, 0 plus 1, okay, minus 5. And here I don't have as complicated of a situation, so if you'll let me kind of sneak a little bit of a shortcut into here, this is going to be just 1, absolute value is 1, and then 2 times the 1 gives me a 2. And well, I probably could have cheated even further than that, but then 2 minus 5 is of course -3. So again, I could write that as 0, -3 if that's how the question was being asked of me, but again, I'm going to take the lazy route out and go with the -3, assuming that the 0 is the other half of the coordinates of my point. Okay, now moving on to graphing using symmetry. Well, we have three basic types of symmetry that we're going to talk about: y-axis, x-axis, and origin. So let's talk about y-axis first, just because I feel like it. Alright, if we have y-axis symmetry, and then basically what that means, and let's change colors here to make it all dramatic looking, but if I'm symmetrical to the y-axis, then the y-axis right here is our line of symmetry for well. Basically what that is, it's basically a mirror. Okay, so my graph is looking at that mirror and he sees its reflection on the other side of that mirror. So whatever I have here on the right, I basically going to have that same thing on the left. And you can do this by transferring coordinates of points around if you'd like, or whatever makes sense to you. But first of all, let's get another color. And well, if I have 0, 0, well, it's right up against the mirror. And basically, if you stood in front of your mirror and pressed your nose against the mirror, well, your nose on the mirror is its own reflection. So that's not very, dramatic, other than that, little spot you leave on the mirror, which, ew, gross. Anyway, moving along, we can see this is pretty much linear on what it actually is. So let's just kind of go to the end point of this. And I've got this endpoint over here that is, well, if you want to count things over, this is 3 over, and then 1, 2, 3, 4, 5, 6 up. Well, if I'm a little bit away from a mirror, when I look at my reflection looks like it's a little bit away, and in fact the exact same distance. So any 3 units this way is going to give me a point 3 units that way on the same horizontal line. And then I can just kind of connect the dots, and with a linear thing here being a linear thing there, just want to kind of duplicate that. And then just repeat that with the other endpoint down here. Alright, so I see this point, and I can go 1, 2, 3, 4, 5 units away, so I come again in the same horizontal line and just count 5 units over, and then just connect the dots as appropriate. And then again, it should look like you could fold the graph in half over that mirror line I said earlier, and the two sides should meet up with each other. And that would be a graph with y-axis symmetry. Okay, now moving on to my next example, you'll notice I didn't do one with the x-axis symmetry because, quite honestly, if you can do the y-axis, folding things from right to left or vice versa, you should be able to do the x-axis, which is folding things from up to down or vice versa. So I'm going to move on to something that's a little more unique compared to the other two, which is the origin symmetry. Well, first of all, of course, if you're talking about the origin, you're not talking about a line like the axes are, you're talking about a point. So in order to pull off symmetry to a point, basically it's a rotation, or I'm just going to use a little more of a layman's term here and go with a spin. So I need to be able to spin whatever graph I have 180 degrees and have its reflection, well, not really a reflection, but have the result of that 180 degree spin sitting on the other part of the graph. So here, if I have the first quadrant chunk of graph, I'm going to spin that thing, and if I go 180 degrees, that basically is going to put me down in the third quadrant. Okay, I pick first versus third quadrant here to help illustrate. Well, first quadrant is generally 2 positive numbers. Third quadrant is 2 negative numbers. So in order to pull off the spin in kind of a sort of algebraic-ish manner, all you really have to do is take the coordinates of any point on the original, take the opposite of both coordinates, and then replicate the new negative version of that in the other quadrant that it ends up. In this case, it'll be the third quadrant. So really, I just have 3 points to be concerned about here. I have 0, 0, which admittedly, taking the opposite of 0, 0 is still 0, 0, so not very dramatic so far. But now I've got 3, 6 for the turn right here of my graph, and the, of course, opposites of that gives me a negative 3, and then negative 1, 2, 3, 4, 5, 6, and gives me a point there, and hopefully I can draw a reasonably straight line to connect the two. Try that, there we go. And then if I look at the coordinates of this guy, well, this is 4, 5. Oh, check that, that's 5, 4. Okay, so the negative version of that is going to be negative 5, negative 4. So 1, 2, 3, 4, 5, 1, 2, 3, 4, puts me down here. And again, maybe not blatantly obvious as I started doing this, but hopefully now that I've finished it, you can kind of imagine this half of the graph spinning 180 degrees landing on here, and likewise this new version of the graph that I've drawn, or a new part of the graph I've drawn, if you spin that 180 degrees, it'll land straight on top of the blue as well. So there would be completing a graph if we'd known it has origin symmetry. Alright, I kind of hinted at it with the last slide, but algebraic test for symmetry, we can kind of do some playing around and kind of generate our symmetrical points to one part of a graph to another using some sign changes. And here's basically a summary of all those rules. And I do want to spend a couple seconds explaining each one, so here we go. Okay, if I'm going for x-axis symmetry, okay, well basically an in order to pull that off, I can take any sort of y and replace it with negative y to have x-axis symmetry, and hopefully visually this will make a little sense. Alright, notice I'm not messing with the x, but if I can have any x value that gives me a positive y, I should be able to get that same negative y out of it. So that's what we're going with here. So if I have x-axis symmetry, any point here, let's pretend that that's the point 3, 1. It looks pretty reasonable. So the negative y is still going to come out of the 3 if I choose to use a negative 1 on the y. And likewise here, if this is like maybe 4, 4, well, I'll still have a positive 4 for x, but then I'll have a negative 4 for y. And then again, if I just do my best job recreating this graph, well, I missed by a little bit, but you can kind of see that this looks like I can fold the red onto the green or vice versa. You know, give me a little bit of a margin of error here because in fact I am human. Alright, going with the next one, if I can replace x with negative x, and maybe this one makes a little more sense because this is more traditional what we talk about with symmetry, because normally we work with functions, and this guy on top is definitely not a function. So maybe this will make more sense. Okay, replacing x with negative x. So if I pick some x value here and it generates this y value, well, if I plug the negative x in, it should still give me the exact same y value. So 3 gave me 1 for y, negative 3 gave me 1 for y again. Cool. 4 gave me 4, but then plugging negative 4 should also give me a positive 4. So again, I get something like that, and then of course connect the dots in a semi-reasonable way. It gives me, again, something that in theory looks like you should be able to fold one onto the other, red onto green or green onto red. Then the origin symmetry, again, it's a little bit different because you're talking about a point instead of a line, but basically replacing each of them with the negative versions of each other give us, you know, another point on the graph. So now again, kind of what I did in that last example, 3, 1 should give me negative 3, negative 1-ish. And then likewise 4, 4 should give me negative 4, negative 4. And again, now we have that sort of spin sort of appearance of the graph. So kind of that's what's going on as far as these things go. Okay, so I'd like to just put what I just said into action, a little bit of algebraic work to back up that visualization I gave that hopefully made some sense, but if not, hopefully this makes some sense, one or the other. Hopefully it works for you. But anyway, again, basically for rules from the other slide was if I have x-axis symmetry, then basically what I want to do to test and see if it has it is replace y with negative y. Alright, now I've purposely picked this equation because you should recognize that as a parabola. So the negative 7 lets me know it's going downward and is pretty darn skinny, and then the plus 5 just lets me know that it's slid up on the y-axis. So this guy should be nice and symmetrical to the y-axis, but should not be symmetrical to the x. And again, being a parabola, hopefully you can sort of visualize that that's not going to be symmetrical to the origin either. Well, heck, let me give a quick little rough graph of this thing. Okay, it should be sliding up on the 5, and then it should be this super skinny parabola. Okay, well clearly this isn't folded over the x. It is, hopefully, I know it's not a great picture, but folded over the y, and then it's definitely not spun 180 degrees to match onto itself. So what I'm looking at to have answers is no, yes, no, but let's do the work to back it up. Okay, again, x-axis symmetry. We replace the y with negative y, and then roll out the rest of the equation. Okay, and one thing that's a good idea to do in this case is if it's y equals, or just pick one side really, get it to be what it started with and see if the other side is also what it started with. So here with this negative y, I want to get rid of that negative 1, so I'll divide both sides by negative 1. And now that gives me y equals now a positive 7x to the second and now a negative 5. And that is definitely not what we started with. So as far as x-axis symmetry, well, knowing that it's a parabola, we should have been able to say no from the start, but then there's the algebraic reasoning that I don't get the original equation by plugging in negative y. Alright, change color just for effect here, but now for y-axis symmetry, okay, our test here is take the x and replace it with negative x and see if you get what you started with. And so again here, now the y is remaining untouched, equals negative 7, now the x is getting replaced, so negative x squared, and then plus 5. Okay, and, well, y equals negative 7, so the y is what I started with, so that's not so bad. I'll just work out the right side. And we have negative x squared. Well, negative x times negative x is x squared. And then we have a plus 5. And again, now this y is by itself again, so I should be able to look at the left side and feel happy. Looking at the right side, this is exactly the same thing as this. So again, with the parabola, we kind of had that going, especially since it didn't shift off of the y-axis as far as the vertex goes. But since we did end up with the exact same equation by doing that substitution, yes, it definitely does have y-axis symmetry. And then for the origin, let's go green here. Okay, I'm going to replace both. So I'm going to replace the y with a negative y, and I'll replace the x with a negative x. And again, the plus 5 is just along for the ride, at least right now it is. And so first thing, before I try to get rid of this negative sign, I do want to work out the right side. So negative y equals negative 7x squared plus 5, and that should look familiar because we just did it 3 seconds ago over here. But now we have to divide through by the negative 1 to get that y by itself, so we actually have a good way of comparing the original equation versus the work that we end up with. And so now this is a positive y, but now we do have a positive 7x squared, and now we again have a negative 5. So since this is not the exact same thing as the original, we, again, what we knew was going to happen is no. So in terms of our symmetries, not the x, yes on the y, but no on the origin. Okay, so the last one we can kind of tell the answers before we started, so I wanted to take a look at one where the answers wouldn't be quite so obvious. Xy to the third equals 1. If you know what that looks like before I talk about it, then kudos to you. But anyway, let's try those algebraic steps and see what's going on here. Okay, would that guy be symmetrical to the x-axis? Well, let's find out. Okay, we're going to replace y again with negative y. And one thing you can kind of do is just, if you're finding x, mess with the y. If you're finding y, mess with the x. And if you're doing the origin, well, mess with both. It's just maybe an easy way to remember it, because it does get a little bit backwards here. As you're finding one, you mess with the other variable, but maybe you can use that to your advantage to remember which one to do. But anyway, here we go. Replacing the y with negative y gives me x negative y cubed equals 1. Alright, well, if I cube a negative, I still get a negative answer, so maybe showing more steps than you want to see, this becomes x negative y cubed equals 1. Okay, notice the 3 kind of jumped on the inside because the negative is going to be there after you cube it. And then from here, okay, we end up with negative xy to the third equals 1. And again, I'm going to get rid of that negative just so that I turn my variable side, the left side, whatever you want to call it, into the original, then I can compare what happened on the right. I've got xy to the third equals now negative 1 instead of the original positive 1. So as far as the x-axis, nope, this guy is not symmetrical to the x. Okay, moving on to the y-axis. Again, I'm going to replace my x with a negative x and see how that plays out. Alright, so now I have negative x times y to the third equals 1, and this is going to look real familiar in just a second. So kind of cleaning up the mess here, which is basically dropping the parentheses, I get negative x times y to the third equals 1, and then I'm not going to bother showing the work because we just did it. But this gives me now dividing through by negative 1, xy to the third equals negative 1, and just like in the last one, that gives me something that is not symmetrical that way. So not in the x, not in the y, but hey, there's always hope for the origin. So we're going to replace both. So my x becomes a negative x, my y becomes a negative y, I still have my cube, and that equals 1. Now the good news here is the negative x remains a negative x, again showing too much work like I did in the last one. Negative y times negative y times negative y gives me negative y to the third equals 1, and now I have this where the two negatives cancel each other out, giving me x y to the third equals 1, which is in fact the exact original equation. So in fact this guy, as messy as he is, and whatever the heck the graph looks like, feel free to throw that in a calculator and graph it. Yeah, that is symmetrical to the origin. Okay, my last example for this video, you may cheer if necessary, is going to be working on the equations of circles. Now granted, there are some very simple problems that you can ask about the equation of a circle, like if I give you the radius and the center right from the start, so I'm not going to waste your time on those and do the kind of worst case scenario here as part of the video. Okay, if I give you the endpoints of the diameter are, these points, 5, 8, and negative 1, 2, you should be able to come up with the equation of that circle. Well, granted, it's maybe not the most obvious thing in the world, but if we kind of, and again for you visual people, I'll just draw a rough sketch here. If I've got 5, 8, that'll be somewhere around there, and then negative 1, 2 should be something around right there. So there's a rough, and I mean rough, like nobody's business, version of my circle, and okay, if I connect the two endpoints of the diameter, well, if I do that, of course, I know the center of that, or better yet, the midpoint, is going to be the center of my circle. Hint, first thing we're going to want to do is use the midpoint formula and figure out that midpoint. There are some other orders you could do some of this stuff, but I'm going to go the midpoint route first. So, of course, midpoint, I'll choose capital M for that. Okay, add up your x's, add up your y's, divide by 2. So 5 plus negative 1 over 2, comma 8 plus 2 over 2. And if you pardon me and let me do a little bit of shortcut here, this is 4 over 2, which is going to be a 2. And then 10 over 2, which will be a 5. Okay, so now my midpoint is 2, 5, which is the center of my circle. And realistically, as soon as I know that, I know the equation of my circle. Let me come down here in the low left and write this. I know it's going to be x minus 2 squared plus, and then y minus 5. Quantity squared equals the radius squared. So really, I just have to fill in one number after I've done the midpoint formula. Unfortunately, to get that one number is going to take more work than what we had to do so far. Alright, now we have a couple options. I could find the distance between the two endpoints of the diameter, and that'll be, well, obviously the diameter, and I'll have to divide it by 2 to get to the radius, because that's the number that I want. Or what I like to do personally is I just take that midpoint that I just found, and then pick whichever of the two original points looks nicer, and then I do the distance formula on that. The good part about that is then I'm finding the radius immediately, and I don't have to remember to divide my answer by 2. So that's what I'm going to go with. Radius is actually equal to d, if you want to think of that as distance and not diameter. Important distinction, especially for this problem. Alright, so there's my big square root. Okay, I'm going to use my 2, 5, and then I like the 5, 8. That one looks a little nicer because it doesn't have a negative sign in it, although it really won't matter. So, here we go. Subtracting my x's, 2 minus 5. Squaring that, plus 5 minus 8. Alright, so, okay, well, if you permit me again to take a little bit of a shortcut here, 2 minus 5 is negative 3, squaring that is 9. 5 minus 8 also negative 3, squaring that is also 9. So I've got my distance, or my radius, being the square root of 18. And instinctively you might want to go, ooh, well, we can simplify that and we'll get out to be 3 root 2. But remember, what's about to go right here is the radius squared. So I would much rather square the square root of 18 than 3 root 2. Because here all I have to do to square this is drop the radical sign. Here I have to get the 2 and then remember to square the 3, which is one of those things people tend to forget to do. So I just stop here, don't bother simplifying radical since I don't need that kind of an answer, and get an 18 as the number that I put in my circle, which is then finally the entire equation of my circle. Alright, there it is, guys. Thanks a lot.